Hi, I'm Guang from NS High School. In this lesson on the techniques of definite integration, we are continuing from the previous lessons. Well, in previous lessons, we started to look at our divergence theorem, or maybe some of you know it as the Gaussian theorem, or even the Ostrogradsky's theorem. So in this lesson, it's somewhat of a continuation of it, or even considered some kind of variation of it, alright? Since these things, they can be pretty related, right? So let's take a look at what we have over here. So this question here is actually made of two different parts. So firstly, we suppose that this f vector is some sort of del phi, where this phi is a single valued continuous partial derivative, right? So what we are supposed to do is to show that this work done of a moving particle from one point P, let's say, to another point Q, and when we're trying to find this work done, it will actually be independent of the path between P and Q. So no matter which direction you take from P to Q, whether you take multiple loops around, the final result, as long as it starts on P, ends at Q, it will always be the same. Alright, so let's take a look at how will this work. So let's start off with work done. Now, let's say this is part 1. So, work done. How will you find this work done? So, in order to find it, you'll probably use some kind of integration. Then you have f dot dr, and you go from P to Q, right? So that will be how you find your work done. However, in this case, we are not exactly too sure how do you find this, right? So in this first part, we're actually given that f is equal to del phi. So let's try to use that. Now integrate from P to Q, and here we have del phi, then dot dr vector. Right, so how will this work? Now del, we already kind of know what it is since we have already shown it in previous lessons. So del, we have those partial x, partial y, partial z thing. So how exactly do we make use of this? So of course, after you try to expand your del, then your phi, you can just multiply inside, which you get something like partial phi, partial x, partial phi, partial y, and partial phi, partial z. Alright, so that's the first part. Now afterwards, you just do a quick dot product, since dr vector will basically just be dx, dy, dz, right? So what you will get is, so from P to Q, or if you want, you can also write that this is from x1, x2, x1, y1, z1 to x2, y2, z2. Alright? So otherwise, then you can have partial phi, partial x, dx, plus partial phi, partial y, dy, then plus partial phi, partial z, dz. So, are we able to recognize what kind of form this is? So, if you have been revising all these differentiation and all, then you would probably realize that this is in the form of a total differentiation. So, how exactly would that work? Now, let's say we put in these as x1, y1, z1, x2, y2, z2. So this will just become d phi. Okay, d phi. So does this look any familiar? Now, are we able to integrate this? Well, yeah, of course we are able to integrate this. So this will just be phi x2 y2, z2, subtract phi x1, y1, z1. Okay, so technically this is already shown, but why is this already shown? So the reason why we are actually done here is, well, since you want it to prove that this is independent of the path, so here what we have proven is that in order to find the work done, you only need the initial and the final. So since you only need the initial and the final, there is no variable here that is related to which path it took, and thus proving that it is independent of the path joining the 2 points. All you need are the 2 points, right? So that is pretty much it for the first part of this question. Now, in the second part of this question, which is basically the converse of it that we have to show. So what does the converse mean? So instead of having to prove that it is independent of the path, now you're given that this is independent of the path, and then you have to show that there's something that exists so that f can be equal to del phi. Right, so how do we start working on this? Right, so let's call this part 2. So when we think about this part, to use the fact that this is independent of path C, and in fact we have to show that there is this function phi. So what if we try to think of how can we think of this function phi? What can it be? Alright, so what exactly should phi be? So one thing that might come to mind would be maybe perhaps some kind of integration that you can do. Alright, so that will be kind of what we have here. Since let, so what will we exactly be letting? Phi be equal to, well, some certain thing. So what do you think will this phi, what can we let it become? So yeah, it could be some sort of integration perhaps. So integration, but what do we want this exactly to be? Alright, since we're given that this is independent of path C, that means we can use some sort of initial and final work done of it, and maybe somehow from there get some kind of difference, relationship, something like that. Right, so for this phi that we will see here, what we'll have is actually so something like this. We're integrating along this curve C, and you have f vector dot dr vector. Right, so how exactly will this help us in whatever we're trying to achieve? Right, so of course if you try to substitute in 2 different points, then you can get 2 different forms of it, right? Okay, so the next thing that we might want to take a look at, so let's say when we change it, we only change your work done in one specific coordinate. For example, you just only change in the x coordinate. Right, so how will that work? Let's take a look at this. So let's say we change this in the x coordinate. So what happens when we change it in the x coordinates? Maybe some sort of definition of differentiation of sorts? Well, you just let a few different things. I mean, limits. So, limit. Since we're using x, let's just make it convenient, and we just have delta x approaches to 0. So, since now we have this, what exactly will we think of? So of course, then there will be some sort of phi. Well, since you're changing in x, that means you can have x plus delta x first, and then of course, depending on what kind of thing you might have, then y and z and so on. And then you have to subtract, of course, the original x, y, z for its difference. And then this difference will then be divided by delta x. Right, so this is what we are seeing so far. Now, how do we continue this? Right, so how about we think about the original thing that we let it be. So when we think of that, let's say we put limit delta x approaches to 0 again. So some sort of integration. Now this time we actually had to try to consider what the boundaries could be. Well, in this case, what could these boundaries be? So let's say we're using your initial point as x1, y1, z1, alright? So this is your initial point, and then your ending would be whatever's inside here. So x plus delta x, y, z. And then of course here you have f dot dr. And then for the second part, we do the same thing. So you have minus integrate x1, y1, z1, and on top you have x, y, z. Right, and then here inside is f dot dr. Then of course you have to divide this by delta x. Okay, so now that we have this step, how do we continue this? So are there any sort of ways that we can kind of combine these two these two integrations? Well, if you have learned a bit of integration before, then you might realize, yes, we actually can. Since this is a minus, then you can reverse these two, so it becomes from xyz to x1, y1, z1. And now since this starts at x1, y1, z1, and this ends at x1, y1, z1, we can essentially stitch these two together and making it, so limit delta x approaches to 0, so integrate from, now this will be from x, y, z to x plus delta x, y, z, right? So that will be what your new thing would be. And of course inside you can still keep it as f dot dr, although, well, you can actually change it into something different. So why exactly can you change it into something different? Now if you look at something above, you might realize they all have 3 components each, x, y, and z. But what are we changing here? In this case, we're only changing the x coordinates. So what? Well, that means we only have to consider their x components. So integrate from x, y, z to x plus delta x, y, z. If you're only considering the x components, then you have fx dx. And then this will be divided by delta x. Now, does this form look familiar to any of you? Since if you have studied calculus in a bit advanced, you might have heard of something like a mean value theorem, which then you can apply here again. And what will you get? You actually get fx. It's kind of interesting, isn't it? So going from partial phi partial x to getting fx. Now, since here your x, y, and z, there is no difference for all of them, that means similarly, partial phi partial y will be equal to fy, and partial phi partial z will be equal to fz. Right. Well, so what? What can we exactly achieve from here? Okay, so once again, we can continue to take a look at things around here. Well, now that we have these three, fx, fy, and fz, so what will be so special about this part here? Since right now we want to show that f vector is actually del phi. So f vector, what is it made out of? So f vector, of course, then you have a x, a y, and a z. So, I mean, there are a few different ways to represent this. You can represent it as I vector fx plus j vector fy plus k vector fz, or like row vector, column vectors, and all. Okay, so from here, how do we continue? Well, we just had some of these things above, which means I vector, this will be equal to I vector partial phi partial x plus j vector partial phi partial y plus k vector partial phi partial z. Does this look any familiar to you? Well, you can technically try to look above and find what's so similar, right? Okay, so actually, for these parts here, well, that would just be a del phi. Oh, how is it so simple? So, first of all, what is your del? Del, that means you have partial x I vector plus partial y j vector plus partial z k vector. And then phi, you just multiply onto each of them. So that's it. So this will be proven. So that will be how you show both of these parts of this question. Whether you're starting from work done or starting from your definition of differentiation, right? So that will be pretty much it for this lesson. I hope that you can understand them so far. And for these two parts, whether it's a converse of it or not, there is a way to show for both of them. Well, of course, as long as this certain thing you have, this maybe certain f you have, is conservative. Otherwise, there might be differences in x, y, and z, and you can't exactly have enough proof for it, alright? So, that'll be it for this lesson. I hope you can understand it so far, and thank you for your watching.